Yes, and we're live again. Excellent. For those that are interested, I will actually be meeting the famous Derek for lunch today. I hope to be just, not hurt my necks looking up at him. But he came up from Texas, and I don't know. I don't know how safe that actually is for him to be traveling from Texas to New Jersey during a pandemic, but I don't know. That's his deal. So we will be meeting for outside food for lunch today at a proper distance. But I'll be saying, I don't know. He's famous now, so whatever. Anyway, as for today, just to give you, I will have you on a Tuesday, Thursday, Monday, Wednesday, Friday, and then a Tuesday, Thursday. So what is that? 1, 2, 3, 4, 5, 6, 7. 7 days, 7 class periods before midterms. I still have a few concepts that we will be touching upon in the beginning of January, because that's 3 full weeks before midterms. But of course, at least one of those class periods, I would like to spend some time reviewing with you guys. And then the week of the 25th should be midterms. Midterms, of course, will cover everything that we've done since the beginning of September. So please be aware of that. As for today, I wanted to spend some more time with this probability concept that we introed on Monday. Obviously, a lot of this stuff you guys have some basis of understanding from previous years of math, but I want to expand upon that now. I want to expand upon it in a little bit. First, I want to review a couple things. So what I'm going to say, I'm going to post something into the Google Classroom for you guys that are online right now, a PDF that I'm going to present on the board. But in terms of the PDF that I'm going to present on the board, there are a few questions that I would like you to try on your own before we actually get going with this information. So I'm going to post that thing. I'm going to bring up the questions on the board, and I'm going to need all of you to have those notebooks out and open. Let's see here. Click, click. Boom. Come on. There it is. Boom. Not that one. And open. Yeah. Come on. And I'm going to flip this over. Excellent. So for those of you in the chat, obviously the questions that are on the board right now are a bit difficult to see, especially if you're online. I'm going to try to zoom in a little bit and focus this stuff. But if you're watching this online, the PDF was posted into the Google Classroom stream, so you can see that a lot easier. But basically, I would like to focus on question number 1 right here, just as kind of an intro to today. See if this zooms in just a little tiny bit. That's not a zoom, that's a zoom. That's a little better, whatever. Okay, there we go. Question number 1. Now, again, I know it's difficult to see this, so I'm going to suggest that when trying these problems, as I read it, write down the information or write down some information that you think would be necessary towards being able to solve these questions that I have posed for you. So here's the pertinent information. And again, pay close attention to the wording. A survey of families revealed that 58% of all families eat turkey at holiday meals. 44% eat ham. And 16% have both turkey and ham to eat at holiday meals. And then there's a bunch of questions. Now, for these questions, I'm mainly going to be focusing on A, B, and C for the time being. D is kind of a gimme based on the definitions that I gave you last class. So I'm really going to be focusing on A, B, and C for the first little chunk of class. So here are the questions for those of you that may not be able to see as well in the classroom. And of course, if you're online, you can see the PDF. A, what is the probability that a family selected at random had neither turkey nor ham at their holiday meal? That's part A. Part B, what is the probability that a family selected at random had only ham without having turkey at their holiday meal? And finally, part C, what is the probability that a randomly selected family having turkey had ham at their holiday meal? Now, if you're reading these questions, you could be thinking one of a few things. But one of the biggest issues that students typically have is just interpreting what the heck the question is even asking in the first place. This is probably the most difficult part of the probability chapters. What the heck are they even asking of me? So, I want to give you a few minutes, not a whole lot of time, maybe like 2 or 3 minutes or so. And I want you to take your shot at parts A, B, and C. Hold on. Yes.
Here's our class.
Okay.
We had to be our trash. We also have a lot of.
They're passing out candy for those of you in the live stream.
You're right. Thank you.
Okay. I got you. All right, cool. All right. Oh, you were saving our class for last.
Yes.
Okay. Now it makes sense. I thought for a minute, I'm like, do you need the pass to go back out? Like, all right, cool. All right, so here's what you missed so far. I'm giving them a couple of minutes to try parts A, B, and C to this question. Now, maybe difficult from where you're sitting to see it very well. I did post the PDF into the Google Classroom stream in case that's a little bit easier to see. But basically, it comes down to a few pieces of information. They give you that 58% of families eat turkey, 44% eat ham, and 16% eat both. And that's all the information they give you. And then they ask the following questions. What is the probability that they ate neither one of them? What is the probability that they ate only ham? And what is the probability that a family having turkey had ham? Yes. I'm going to give you guys 2 or 3 minutes. See what you can do. Your final answer, I would prefer it written as a decimal. Of course, calculators are on the Chromebooks for the most part, but I would prefer it as a 3-digit decimal. But even if you don't have the calculator to do it right now, you could at the very least set it up with how you were supposed to calculate it. So take a few minutes. Let's see what we do. Excellent. So here's what I got so far. This is the information that they gave me. They gave me that the probability of eating turkey is 58%, the probability of eating ham is 44%, and the probability of eating both is 16%. That's all that they gave me. The first question is asking something quite weird. And there are a few different ways to go about getting the answer of what is the probability that they ate neither. There's a few different ways to go about it. Let me show you one of those ways. Now, just because I'm showing you one of those ways doesn't mean that this is the way that I want you to do it. It's just an example, and then I'll show you another way of potentially visualizing it in a few moments. First, let me find the probability of eating turkey or ham. Now, this is a formula that I gave you. Finding the probability of events A or B comes down to, well, the probability of A plus the probability of B minus the probability of A and B. Oh, this should be the probability of A plus the probability of B minus the probability of A and B. I don't know. Let's just see. 86. Or 0.86, I should say. Now, that is not your answer to part A. That is not your answer to part A. It absolutely is not. What that 0.86 represents is the probability that they would have one or the other. And the question, the way that it is worded, if I could bring this back, ba-bow. Oh, wait, it didn't go. There it goes. And the way that the question's worded is, what is the probability that a family selected at random had neither turkey nor ham? So one could just simply take the complement of 86% to get 14%, which is the answer to this question. That's one way of potentially handling a question like this. Not the only way, just one way. Here's an alternative way. An alternative way of getting the answer to said question, if you needed to visualize this thing, could be to create a Venn diagram. Anybody create a Venn diagram? Okay, that's fine. It's just one way of visualizing the problem. So if you would, copy down said Venn diagram. This would be turkey. This would be ham. And I'm going to put a box around it for a very particular reason. I'm going to put a box around it. Now, the interesting thing is, I can't just put 58% into the turkey circle. I can't. And I can't put 44% into the ham circle. I can't. I can put 16% of right in the middle. I can put 16% absolutely dead spot in the middle. But I can't use the 58 and the 44. 16% have both. The turkey circle, the entire turkey circle, should total 58%. What am I going to put in this blank spot? 42? Yeah, I believe that works. I had to do math in my head for some reason. I don't know why. 42%. Because that entire turkey circle, or 0.42, I'm going to put, doesn't matter. That entire turkey circle should add up to 58%. By that same logic, this should be 28% right there. Now, when it comes to a Venn diagram, it comes down to four possibilities. A basic Venn diagram. Four possibilities. Either you're in the first circle by itself, you're in the second circle by itself, you're in the middle, or you're not in either circle. Those are the four possibilities here for a Venn diagram, and they should add up to 100%. And I mean, I don't know, I'm just showing this for the fun of it, but 0.42 plus 0.16 plus 0.28 don't add up to 100%. They only add up to 86%, which means 14% lie outside of the Venn diagram, neither ham nor turkey. Yay. Like I said, there are multiple ways to kind of visualize this problem. Now we get a little more crazier. Part B. Part B, what is the probability of only ham? Well, if I go over here, yeah, what is the probability that a family selected at random had only ham without turkey at their holiday meal? Well, like I said, there's a couple different ways of going about it, but I'm pretty sure the answer is just 28%, because we've already done the work for it. The work was done in that Venn diagram. Only ham, no turkey, 28%. Venn diagrams can come in handy when it for some of the more basic problems in probability. They can come in handy when you're just comparing events A and events B. Yay, only ham. I'm not a fan of only ham. Question. Would you consider it a faux pas if you were to take a slice of turkey and dip it in mashed potatoes before you ate it? You said no. Some people just gave me some really disgusted looks.
That's so good. That's good.
I'm just saying. You can't see their faces. Anyway, back to this. Part C. Part C was probably the craziest, because here's the deal with Part C. The answer to Part C is none of these numbers. The answer to Part C is none of those numbers. None, not what, so, not, anyway, back to here. What is the probability, Part C, what is the probability that a randomly selected family having turkey had ham at their holiday meal? Now, this is a weird question. I'm going to write down something, and then I'm going to reveal it in a moment, because I need you to do the proper interpretation here. Kapow! Look what I wrote. What the heck did I write? Ham given turkey. Given that you have turkey. Given that turkey is already on your table for the holidays. What are the chances that you have ham? The given event is what it is. It's given. It's happened. It's past. You walk into a family home. Doesn't matter whose it is. You look at the table and there's a turkey. You're like, oh, look, they clearly have a turkey. Given that they already have turkey, given that I can see the turkey, I wonder what the chances are that they also have ham. That's what this question is asking. Turkey's a given. Turkey's a guarantee. You know our national bird is supposed to be a turkey? Some of you were nodding yes, some of you were giving me weird looks again. Did you not know that our national bird was supposed to be a turkey? Benjamin Franklin wanted it. He wanted a turkey because they were cunning and smart birds, whereas the bald eagle was kind of dumb, and it was just kind of showy. Guess which one we chose? Anyway, back to this. Now, here's the deal. I gave you a formula last class, and I'm just going to write it out with the words ham and turkey in it. Here we go. My son is a turkey. My daughter is a ham. Anyway, I'm going to get in trouble. The probability of turkey and ham divided by the probability of turkey. This is the calculation that has to take place. This is the formula that I gave you last time. If you have the probability of B given A, you find the probability of A and B and divide it by the probability of A. You always divide by the probability of the given event. In this case, Turkey. And knowing all of that information, we're like, oh, happy day. I know that stuff. This should be equal to 0.16, which is the probability of both, divided by, now mind you, the bottom of that fraction is the probability of Turkey. The chances that they have Turkey are 0.58. You would not use the 0.42. The 0.42 represents only Turkey and no ham. But if I'm talking about just the probability of Turkey, no strings attached, then you are counting families that, yes, only have Turkey and families that have both. So you have to account for that. That's the 58% they gave you at the beginning. If you did this calculation correctly, it should spit out approximately 0.276. And yeah, I say approximately, obviously, but you know. If you walk into a household and there's a turkey on the table, then there's approximately a 27.6% chance that they also have a ham. Fun stuff. Anyway, yes.
Question B.
Yes.
What would that equation be? Like if we didn't have the information from A,
Okay.
what would that equation be?
I got you. Well, let me, okay, I'll put it right here. I was debating on where I wanted to write it. Okay. In this particular instance, it's not so much that there's like a given formula per se, because there's no official formula for it. But if we think about it logically for a moment, we take the probability of ham, which in this case, I believe was what these two numbers, which was what, I can't even think, 44%? No. What was it? Yeah, it was 44%, right? 44% eat ham. Right. I couldn't think for a second. The probability of ham, which was 44%, which I'll write it over here, minus the probability of both, which was how we filled out this Venn diagram. And that's literally what you would do. It's how we figured out that Venn diagram. We took the 44%, which was the probability of ham, and subtracted the 16% to get the 28%. So, yeah. I don't know. I haven't really ever thought about like a formula. I've just always thought about it in terms of like, let me just fill out the Venn diagram and it'll all just kind of fall into place. And then I high five myself. I don't high five myself. That'd be weird. Anyway, back to here. Now, by the way, part D, I know you can't really see it that well. I'm going to scroll up a little bit. They asked the question, are having turkey and having ham disjoint events? What is the other phrasing for the word disjoint? She's trying, yeah, mutually exclusive. Mutually exclusive. And the only way that you're going to have two events that are mutually exclusive or disjoint is when that Venn diagram has no overlap in the middle. Imagine, I'll bring this back over here. Imagine for a moment that the middle of this Venn diagram was empty, 0%, no overlap, meaning you could literally separate the two circles and nothing would happen to the percentages. That's the idea of being disjoint or mutually exclusive. The only way that that's going to happen is if this number in the middle is 0%. So the question is, are they disjoint? No, they're not. Why? Well, because the probability of both is 16%. Yes, the only way that they're going to be disjoint is if the probability of both was 0. Okay. Now, I'm going to ask a few additional questions in regards to number 2, because they ask their question, which I have not given you the definition just yet. I have not given you the definition just yet for number 2, but I am going to ask a few additional questions. So let's see what this says. Many school administrators watch enrollment numbers for answers to questions parents ask. Weird, I don't know. Some parents wondered if preferring a particular science course is related to a student's preference in foreign language. Students were surveyed to establish their preference in science and foreign language courses. Does it appear that preferences in science and foreign language courses are independent? Now, I have not given you the definition yet to answer that particular question. I'm going to focus on a different question first. Pick a foreign language up here. Pick one. Okay, French. We surrender. Anyway, now pick a favorite science. Chemistry. Okay. It doesn't matter, because the numbers are going to be slightly different no matter what we do. But here's the deal now. What is the probability that someone would prefer French given that they prefer chemistry? Let me write that down. What is the probability that someone would prefer French given that they prefer chemistry? Now, there's a few different things to go along with this, because I want to show you, using that table, I want to show you how the different numbers would be calculated. So I'm going to write a few different calculations underneath of here. First of all, I'm going to write down the probability of French. I'm going to write down the probability of chem. I'm going to write down the probability of French or chem. And I'm going to write down the probability of French and chem. These calculations are very important to distinguish, because each of these 5 calculations that you have up here are going to give you different answers, or they should give you different answers. Maybe randomly they might accidentally give you the same answer. That's just circumstances and coincidence. Let's start with French. First of all, according to this table, how many total people prefer French? Total people. Out of what? One what? 136. Hold on. 34 out of 136. I put that right there. 34 out of 136. 34 divided by 136. That is literally equal to 0.25. I mean, it's right on the dot. Good for them. All right. Let's look at the table again. What fraction would represent those who prefer chemistry? What fraction would be those who prefer chemistry? 51 over 136. Now, those are very basic questions about the entire group of people, the entire group of students. Just very big, no strings attached. The probability of preferring French, which is a total of 34 out of 136. The total preferring chemistry, which would be 51 out of 136. 51 divided by 136, which is 0.375. Oh, there is a 6th calculation that I got to do, but I'm going to save that for later. I wanted to put all of it. You'll see. Now, or French or chemistry. When I hear that word or, I usually think to myself, okay, I got to use that formula that has like the adding in it. The adding, I got to add stuff together. Okay. French or chemistry. You got an idea? How'd you get 85? Okay, hold on. Where's my marker? Boom, boom, boom. So I'm going to put them in the fractions, just so you know. So you were like 34 out of 136 plus 51 out of 136, and you got 85 out of 136. You got to catch it. What am I telling you to catch? Huh? You got to subtract the 16. You got to subtract the 16 because technically you have counted them twice. You have counted those 16 students in the group of 34, and you have counted those 16 students in the group of 51. This would be the probability of French plus the probability of chemistry minus the probability of both, which in this case, 85, it says 69. Okay, some people are barely nodding yes, but okay, cool. So hold on, let me write this down. My microphone, everything fell apart. So I already forgot those numbers. It was 34 plus 51 minus 16. There we go. Cool. It was 69 out of 136. Japan. 69 divided by 136. Boom. Which gives you approximately 0.507. Coincidentally, we've already figured out the bottom calculation. The bottom calculation was 16 out of 136 because of those 16 students who take both, which in this case is 0.118 it rounds up to. Now, when I hear that word and, I think of what operation? If I have to do French and chemistry, what operation should I be thinking of? Ooh. What did those formulas tell you to do? What operation was in those formulas? To multiply two things together when you hear that word and. French and chemistry. Now, the thing is, we got the table right off the bat, but here, how many different formulas did I give you for and? How many did I give you? I give you two formulas. And what was the distinguishing factor between whether you used one or the other? Which we don't know. We don't know. Let me repeat what just happened here. Let me repeat exactly my logic of statements. First of all, the question is French and chemistry. French and chemistry. Okay, I got to multiply stuff. Ooh, but I gave you two different multiplying formulas because the distinguishing factor between those two multiplying formulas was whether the events were independent or dependent. We don't know. We don't know if they're independent or dependent. So we have to rely on the table that they gave you, which they don't always give you. But in this case, we do have to rely on that table for this thing to work with the way we want it to. 16 out of 136, because we have the exact numbers. In fact, check this out. I'm going to bring this up real quick. Japan. There we go. 16 out of 136 was clearly the answer to French and Chem. But let's just pretend for a moment that I did, I don't want, come on. 34 divided by 136 multiplied by 51 out of 136. Come on. I hate this calculator. 34 divided by 136. 51 divided by 136. Oh, that answer is actually pretty close. I mean, it's not spot on, but it's pretty close. I wonder if that has ramifications for a definition in a few moments. Anyway, we'll get there. Back to here. French given chem. Oh, you can't see it. French given chem. Actually, no, it's at the top of the page. I want the table. French given chem. Given chemistry. Given that you are only looking at a group of chemistry students. Given that you have walked into a chemistry classroom and these students obviously are taking chemistry. Given all of that, the chances that they are taking French. That's what the question's asking. If you want to figure that out by just looking at the table, you take the given event, in this case chemistry, and you section off that information. Given that you are only looking at 51 chemistry students, the chances that they are taking French are 16 out of the 51 students. That's how we handle a given probability, a conditional probability. 16, oh, you can't see it. 16 out of 51. Which approximately is 0.314. It rounds. Now, I do have one more statement to kind of give. I'm actually going to reverse them to kind of nail this point home. I want to find the probability of chem given French. If I could spell French today. The probability of chem given French. Now I'm reversing them. Now I'm reversing the condition of the problem. The condition of the problem is now given French. Given that you've walked into a French class. Given that you are only looking at French students. And how many French students are there? There are 34. Given that you are only looking at those 34 students, the chances that that group of students would be taking chemistry would be 16 out of 34. Flip this over. In this case, the bottom of the fraction changes. Now it's 0.471 is what it rounds to. There's a lot of different things they could ask you. There is a lot of different stuff they could ask you. I want you to be aware of it. Definition time. Here's the definition that's going to help with this question. If events A and B are independent, then. Now, there's a few different alternative definitions that people do for this, but here's one of the more basic ones. Then the probability of B is approximately equal to the probability of B given A. If events A and B are said to be independent of each other, then the probability of B would be approximately equal to the probability of B given A. Yay. Technically, we already have some of these answers. So hold on. I'll do the first one. The probability of chemistry is equal to 0.375, which we found that on the table. And the probability of chem given French, is equal to 0.314. Ooh. Interesting. Now, there's probably a few different things that we could check. We could probably even check chem given Spanish. Let me write that down as well. The probability of chem given Spanish. Now, you'll have to trust me on this one. Chem given Spanish, given that you were only looking at the Spanish class. Oh, did I mix those up? Yeah, I totally mixed those up, didn't I? It wasn't 0.314. Yeah, Chem Gibbons French was this bottom one. It was 0.471, right? Cool. Yeah, it's 0.471. This is what I get for doing the work beforehand and not looking at it. Chem Gibbons Spanish was approximately 0.343. You know, just trust me on that one. Question. Are those numbers approximately equal to each other? They're not. To be approximately equal, they got to be a lot closer. If they're going to be approximately equal, it's got to be like maybe like what, 37% and like 38%. Then I would say, yes, they're approximately equal to each other. But 37% and 47%? Ugh. No, they're not approximately equal to each other. So what can we say? No, we can't say that, unfortunately. I know. Fluffy language. That's the best we can do. I'm going to write that down, but that's the best that we can do here. The question was science and foreign language. Are they independent of each other? We can say there is evidence. This marker's dying on me. Go away, marker. There is evidence to suggest that science and foreign language preference are not independent. Now, again, like you just said before, like one could argue, like, Mr. Murky, can't you say they're dependent? No, unfortunately, you can't say that they're dependent. Unfortunately. Think of it this way. In a court of law, you are presumed innocent until proven guilty. And when they bring down the verdict in a court of law, has the verdict ever been that the person is innocent? No. What are the only two outcomes? Well, the basic two outcomes for a court case. Guilty or not guilty. Notice they didn't say innocent. It's either guilty or not guilty. In this case, it's either independent or not independent. We can't proclaim dependence, unfortunately. And even then, we're only saying we have evidence to suggest it. We're not saying that they are. Fun stuff. Okay. One more thing. Chapow. It's number 3 on this paper. Now, number 3. I'm going to read it, and then I'm going to decipher it. For the purposes of making budget plans for staffing a college reviewed student's year in school and area of study. Of the students, 22.5% were seniors, 25% were juniors, 25% were sophomores, and the rest are freshmen. Did you ever see that O in the middle of sophomore? Did you ever pronounce it? Why not? English is dumb. Anyway, also 40% of the seniors major in the area of humanities, as did 39% of the juniors, 40% of the sophomores, 36% of the freshmen. What is the probability that a randomly selected humanities major is a junior? Show your work. Now, first of all, let me read the question, and then I'm going to make a statement. The question is, what is the probability that a randomly selected humanities major is a junior? I'm going to tell you that the answer is none of these numbers. It's none of them. Absolutely none of them. See, the thing is with this question, they give you a bunch of information. They give you, I'm just going to jot these and I'm going to erase these, mind you. They give you the probability of a senior. They give you the probability of a junior. They give you the probability of a sophomore. They give you the probability of freshmen, although indirectly they give you the probability of a freshman because they say the rest are freshmen. But then they give you these other statements. 40% of the seniors major in humanities. 40% of the seniors. Meaning, if you're only looking at the seniors, 40% of them major in humanities. Given that you're looking at the seniors, 40% of them major in humanities. Humanities given senior is 40%. Now I'm just going to write down one more of these. The junior one, which was 39%, as did 39% of the juniors. That 39% represents the calculation humanities given junior. Here's the issue. The question that they're actually asking is the reverse of that. The question that they're actually asking, what is the probability that a randomly selected humanities major is a junior, is actually the reverse of that given statement. They gave you humanities given junior, and they want you to calculate junior given humanities. It is not a simple question. It is not a matter of just staring at the numbers long enough and hoping that the answer shows its face. We're going to have to dig. We're going to have to dig for this answer. To dig for this answer, I need to go back to my notes. Here's what I'm going to do. Click. Oh, froze like my heart. There it goes. I need you to draw something for me. Let's start here. First of all, to be a senior, a junior, a sophomore, a freshman. There it is. According to the problem, they gave you the following information. They told you that, well, the chances of a senior are 22.5%. The chances of a junior are 25. The chances of a sophomore is 25. And the chances of a freshman is 0.275, because that's the rest of them. Adding up to 100%. Good for them. But then, they said of the seniors, 40% were humanities majors, which clearly means 60% were other. Of the juniors, 39% were humanities majors, and 61% were not. They were other. Of the sophomores, 40% were humanities majors, and 60% were other. And of the freshmen, 36% were humanities majors. I'll zoom out a little. There we go. I know it's a little hard to read at this point. And 64% were other. Let's argue, what the heck is this? This is called the probability tree. And this probability tree is going to be the way we are going to answer this question. The question that they are asking is, what is the probability of having a junior given that they are a humanities major? And the way that we are going to calculate that is using the formula that I gave you at the end of class last time. In order to calculate the answer to this question, we need the following fraction. We need the probability of being a junior and a humanities major, which they did not give you in the problem. You also need the probability of just being a humanities major, which they did not give you in the problem. The only thing that they gave you in the problem was all of this information that I just organized into a tree. Now, for the sake of argument, I'm going to run out of time today. I'm not going to put this into my notes just yet, but I did want to show you how the answer was actually found. First of all, if you want the probability of being a junior and a humanities major, and implies what operation? Multiplication. You simply go along the branches of the tree, 25% times 39% to get junior and humanities. But then, in order to figure out the bottom of the fraction, this is the trickier part. If you're a humanities major, you could be a senior or a junior or a sophomore or a freshman, or implying what operation? Addition. Yeah. So if you want to find the humanities major, and this is why I'm not doing it right now, you would have to multiply along the senior branch in humanities, multiply along the junior branch in humanities, multiply along the sophomore branch in humanities, multiply along the freshman branch in humanities, and then add them all up. It's a fun thing. So, over break, by the way, I'll finish this when we get back from break. Over break, I'm not going to be assigning you things to turn in. Instead, I am going to assign you some suggested reading. I will post that information on Google Classroom, but I am only going to be assigning you some suggested reading so that you can stay sharp and prepared for when we get back. I'm excited. Anywho, I'm going to sign off in the chat. I got another class coming in approximately 30 seconds. You all have a wonderful time. Woo! Click, click, end.